If not, maybe yes, Zhenya.
I have a question for Bo, if he's here. So my question is about singlet constraint, because in 3 dimensions we have natural way to impose singlet constraints via Chern-Simons, but this of course leads to observable predictions for partition functions and so on. But in 4 dimensions there is nothing like that, and the question is, well, can you come up with some experiment that would tell us if just coupling to a mu is the right way to impose singlet constraint?
I'm sorry, I didn't quite hear the sort of the heading of the question.
No, so it's about singlet constraints. So let me just speak up. So in 3 dimensions, you can impose singlet constraints quite naturally by coupling vector models to Chern-Simons.
Yeah.
Okay, yes, but it leads to some log corrections to well, partition function, which you can in principle detect, say, from the bulk if you're able to compute this contribution. So in principle, it's not it's not harmless to impose singlet constraint by hand or just by coupling to anything we want. So can you come up with some kind of experiment, well, mathematical sense, obviously, where we can detect if coupling to a mu is the right way to impose singlet constraints in 4 dimensions? Because as far as I understood, you're working with vector models.
Yeah. Well, I mean, let me approach. Let me say directly that I think of this 4-dimensional case as sort of a toy model, and I'm not claiming that I understand completely what one should do. Still, I mean, it's. Yeah, I mean, there are many ways you can say that this is a toy model, and there are things to worry about. But I mean, formally, the idea would still be that you couple it to a gauge. You couple the scalars to a gauge field, and then take the 0 coupling limit. Of course, that relies a bit on having complementing the model as in super young mills to be conformally invariant, etc. So yeah, I mean it is. I think of this as a toy calculation, more or less. I haven't thought too much about it beyond that. I think my attitude is that large N is a very influential. It governs a lot of the dynamics. So there would be some truth in the statements you can derive, even if you might have to, the validity may not be universal, right? And so yeah, I mean, the precise calculation is in a toy model, I would say.
Yeah, okay, many thanks.
So there is a question by Misha.
I want to ask Matthias. Actually, I want to elaborate on my question that I asked after his talk. Is Matthias around?
Yeah, I'm here.
Okay, so I was asking about higher-span symmetry algebra for free super young mills, n equal 4, which was known long ago, like 20 years ago by now. But then there was a kind of proposal of a dual for the full n equal 4 higher-span, n equal 4 super young mills. It's more recent, it's a couple of years ago in terms of some extended Coxeter higher-spin symmetry algebras. And as far as I can see, the spectrum of fields is pretty much similar to the spectrum of that you predict. The proposal was that this is a kind of stringent version of the higher-spin theory that should be associated with n equal 4 super young mills. So I just wonder whether you can comment on this somehow. I mean, do you have a
I'm not entirely sure how this would relate to one another. I mean, it is. I mean, as you've seen in our description, you have basically this singleton representation, and that and you get these tensor powers, and that's what reproduces n equals to 4. Now, the higher spin action on the worldsheet is not that manifest. What's manifest on the worldsheet is the PSU 2,2/4 action. But on the worldsheet, we don't see the full, I mean, microscopically, we don't see a direct action of the higher spin symmetry. So it's not manifest from the worldsheet perspective directly why you have a higher spin symmetry. So I suspect it's a little bit different than what you did, but it's, but on the other hand, it's a more conventional string theory, right? We just write down a worldsheet theory, and it's like the higher dimensional analog of the worldsheet theory we wrote down for ADS3 + 3, and then we just impose conditions that look at least very similar to what you impose in.
Okay. Yeah, but once you are talking about dual for free n=4 super Young-Mills, this means that the symmetry should be around for free n=4 super Young-Mills, and actually the singletons from that perspective, multi-singletons, also should be around, I guess. I mean,
I'm sure it's around. It's just not that manifest at the moment. I mean, as you know, in string theory, for example, when you quantizing light cone gauge, certain symmetries aren't manifest that are manifest. So in this description, the PSU 2,2/4 symmetry is manifest. The higher spin symmetry is obviously there because the spectrum falls into representations of the higher spin algebra, but it's not manifest because, and it has to do with some sort of more complicated way in which the higher spin symmetry will act on the worldsheet. But that is also true for the case of ADS3 = 3. I mean, for the case of ADS3 = 3, where I think we have a very detailed understanding of how it goes. Obviously, the theory does have higher spin symmetry, but from the worldsheet perspective, it's not manifest. It's only the PSU 1,1/2 symmetry that's the n = 4 that's manifest, but not the full higher spin symmetry.
well, I agree, but I don't think that there are two different duals for the same free theory. After all, they should be equivalents one way or another, I guess.
Probably, but I mean, our description, I think, is what people would recognize as a conventional string theory, right? So it's so what we've written down is a theory that you can recognize as a conventional worldsheet theory, and it has the property that modulo understanding the physical state conditions, you reproduce exactly the spectrum of n = 4 super Young-Mills. So that makes sort of the string picture more manifest.
Well, okay.
Well, in the meanwhile, there is Zhenya who raised the hand again.
So can I ask two questions for the price of one, or do I have to? So I have a question for Matthias. So in lower dimensions, higher spin symmetry is not that restrictive. You know this better than me. That say in 3 you take HS lambda, but the actual symmetry is Greenfield Sokolov reduction of that. But starting from 3 dimensions, we have model synergy-Boyedov theorem and its high dimensional generalization. So in principle, once you have a CFT with higher spin current, you more or less know correlation functions and so on. So do you think the string theory computation of holographic correlation functions can be massaged in such a way that you see explicitly, say, free super Young-Mills correlation functions, not just at the level of the end result, which has to be correct, of course, because of higher spin symmetry, but somewhere earlier on? Thank you.
I think that would be the hope. I mean, we haven't yet done that computation, but what we've managed to do is the corresponding computation at ADS3 + 3. Obviously, there the dual is n = 4 super Young-Mills, but the symmetric orbifold. But in that context, the worldsheet calculation manifestly reproduced the symmetric orbifold. And the reason this worked was, so normally string theory worldsheet calculations are horrendous because you have to calculate the correlation functions on the worldsheet, but at the end of the day, you have to integrate over the moduli on the worldsheet. And normally nobody knows how to do this integral. I mean, this is typically out of reach. Now, what happened for the symmetric orbifold was that the correlation functions on the worldsheet had actually a delta function localization property. Most of the time they were 0, and this integral over the moduli space actually turned into a finite sum. And what it turned into was a finite sum of holomorphic covering maps. And thereby you manifestly reproduced the answer from the symmetric orbifold, because in the symmetric orbifold, you can also write the correlators in terms of sums over covering sets, covering surfaces, holomorphic covering maps. Now, the structure of the worldsheet theory looks very similar. So therefore, we would also believe that in our context, the worldsheet integral will contain delta function localized behavior. And as a consequence, the integral over the worldsheet moduli is again likely to turn into a finite sum. Now, this has been seen before, that when people try to reconstruct the worldsheet theory starting from free superangles, they were also led to correlators of that kind. So we believe that our worldsheet correlators will again be delta function localized. Therefore, the worldsheet integral will be a feasible integral to do. And this is, we hope that it will sort of more or less manifestly reproduce the big contractions of the free theory. So that would be, so we think of this in a sort of more pedestrian manner. So we are not expecting directly to see the higher spin symmetry. What we would expect to see is basically just the big contractions of the free fields of free superangles. And given the structure of the correlators and how it worked for ADS3 cross S3, that seems reasonably plausible, I think. But we haven't done it. I mean, I'm not claiming we know. It's just that you see that how it could work out that manner.
So Xenia presumably has his second question, or not?
Okay, yes. So closely related question. So by this worldsheet formulation, you somehow surpass, well, the necessity for higher spin gravity. But can action for higher spin gravity be obtained as a kind of effective string action, a la Fradkin-Zeitlin, but in this context?
Well, I mean, I think you probably want to ask an even more primitive question. I mean, can you see ADS5 cross S5? I mean, in some sense, you see, I mean, so for example, for the case of ADS3 cross S3, we have this PSU1,1/2 model. At level 1, it looks like these free fields. Now, in retrospect, you know, it's the free field realization of something that looks like at large scale like ADS3 cross S3. But if it's somebody just handed to you this free field realization, it wouldn't be so obvious how it's related to ADS3 cross S3. And in some sense, our description is the same. In our description, ADS5 cross S5 is very indirect. Geometry is very indirect because you're sitting at this very stringy point where you don't yet really know what geometry is. You see PSU2,2/4, so you see sort of symmetries, but it's not that you directly see the geometry of anything. And therefore, at this stage, I wouldn't know how to extract from it sort of the analog of a supergravity action or low energy effective action for the low-lying degrees of freedom. That's in some sense far away from our description. That's not directly, cannot be directly read off from that description. So our vision was that we weren't trying to get this theory starting from ADS5 cross S5. Our hope was that we could identify this very special worldsheet theory that's dual to free superangles, and then in some sense, the second step is to understand how to go from there to conventional ADS5 cross S5. And that would be an interesting question that would correspond to making the radius bigger and so on, and switching on interactions. But that's a far away from it. And as a consequence, it's very hard to see what sort of higher spin theory this, how you would describe it in that language, because the language in which we formulated our worldsheet theory is very far away from anything to do with geometry or anything like that.
Okay, thank you.
So me, maybe I have a naive question. I mean, you mentioned that, of course, then one of the next steps would be to start perturbing, to improve. But so which kind of deformation do you expect to introduce to reproduce? And even much further, how do you expect to interpolate between, hopefully, I mean, as a dream, of course, but to interpolate between the free and the very strongly coupled regime, how from the usual worldsheet to the theory proposed?
Right. So I mean, switching on the interaction is not that difficult, right? Because you know the perturbing field. I mean, that's you know the coupling constant in superangles, because we know which fields, how the fields translate to vertex operators on the worldsheet. It's clear what vertex operator on the worldsheet we will have to switch on. So from the point of view of the worldsheet, what you have to do is you have to calculate a correlation function of, say, a 2-point function of whichever operator you're interested in, with additional insertions of this perturbing field, and you calculate the worldsheet correlator of that, and then you just integrate over the worldsheet coordinates. And as I said before, we believe that these worldsheet calculations will actually be doable because we suspect that the worldsheet correlator will again be delta function localized. So what normally is out of reach will probably be certainly doable. And so my suspicion would be that sort of low order perturbation theory we will get under control. And my suspicion would be that once one understands this calculation correctly, it'll just be manifestly reproducing the spin chain way of doing n equals to 4 calculations. I mean, in some sense, I think this worldsheet theory just wants to reassemble itself into a spin chain description. That's what it's almost certainly likely going to. So when I say it's going to manifestly reproduce it, that'll be sort of probably the language in which it manifestly reproduces it. Now then, we are as smart as the spin chain. I mean, then we can do low order perturbation theory, then we can try to use integrability and so on. But I think to start with, you would just want to see that you can, that the worldsheet theory will just be the string theory way of reformulating superangles in terms of the spin chain.
Okay, thank you. Yes, yes. So I don't know if there's some other questions. Not. Well, then if so, we can start maybe the break a bit earlier. And so, if I'm not mistaken, the conference will resume at 17 Moscow time. So thank you to all the speakers, huh? And we'll see you later. Thank you. Thank you again.